So, I'm Deborah from London South Bank University. My colleagues Stefan and I are going to talk to you about air or liquid-cooled servers, the right product for the right place. And I must add that you can see contributions from three other people, Christina, David, and Steve, who also helped us to put this project together and, to create some results for you. So first of all, I just want to explain carbon and life cycle assessment. The least to the most accurate or comprehensive impact assessment. Carbon footprinting is at best indicative and at worst inaccurate because you're only looking at one metric. And we are covering or presenting results from a more comprehensive study. And you can see here, if you're just looking at carbon, as I said, you're just looking at one metric. When you're carrying out a full or comprehensive life cycle assessment, you're including thousands of different impacts, inputs and outputs, and therefore your results are more accurate. So we took two servers as part of the CEDaCI project, which I led for a number of years. An old server, 2004, which obviously was very energy intensive in use. And if you look at the chart on the left, you can see that operational impact appears to be much higher than embodied impact. So that's really driven the focus on operational energy efficiency. A life cycle assessment of exactly the same product, the next bars along, you can see that that ratio begins to change. And then if we come along a newer server from 2017, more energy efficient, the bars on the right-hand side of the chart show that over life, approximately 4 to 5 years, the split between operational and embodied impact is about 50-50. So this, we believe, is a much, much more accurate reflection of the true impact of servers carrying out these really comprehensive life cycle assessments. So we use this methodology, which is very standard, to compare the impact embodied versus operational impact of two servers, an air-cooled server and a comparable immersion liquid-cooled server. And it's saying coincidental, it was the only option we had, was to take an HPE Gen 10 server and to use an immersion-cooled version of the same server because that's what's on the market. It uses the same Proliant chassis. So the servers are as close in terms of specs as you can get, apart from obviously the cooling components. Now what we found was really interesting. When we carried out our full life cycle assessment, we looked at two air-cooled servers, one with hard disk drives and one with solid state, and then the third liquid-cooled server with solid state drives. And you can see that if we take the highest impact, the liquid-cooled server, if we're just looking at embodied impact and taking that as our benchmark of 100%, the air-cooled with solid-state drives has very fractionally lower impact, and the air-cooled with hard disk drives has a much lower, 93% equivalent impact. So that was quite an interesting finding. Don't forget, this is embodied impact only. It's not including energy. So we wanted to think about where would people be likely to use these servers, what's the advantage, the pros and cons, benefits, etc., or otherwise, of using different kinds of servers in different geographical locations. And we looked at the ASHRAE climate bands for guidance. So we have mid-Europe, South Europe, cold Arctic, hot wet, as in tropical, and hot dry, as in more desert regions. Our baseline server was basically an air-cooled server with 25% energy utilization, 200 watt-hours, etc., over a whole year, and we ended up with 1,747 kilowatts a year. There's a comma in the wrong place, sorry about that. And then we looked at that, but we also based our models not just on the cooling energy for the servers themselves, but the cooling energy in the data center, because that's obviously affected by ambient conditions, be it temperature and or humidity. Now, what we found was really fascinating. We know that the embodied impact of air-cooled servers is lower than that with hard drives, is lower than that of air-cooled with solid state, and that liquid-cooled was obviously beneficial as well, or more preferential than air-cooled with solid-state drives. But you can see when you combine the impact of embodied characteristics, components, etc., with operational energy, we get a pattern that is fairly consistent here. And this was based on a server. We know now that Google and Facebook stroke Meta are saying that they're going to keep servers in use for 5 years. So we based our model on a 5-year lifespan. But we can see some really interesting patterns here. That first of all, the area which has the lowest impact of combined operational and embodied impact is the Nordics, cold Arctic, Norway in particular because of their use of hydroelectricity. Where we can see really high impact, and now these figures are shown as a percentage or in relation to the highest impact, which is in Namibia, which is air-cooled servers with solid-state drives. That's our 100% datum. And Namibia, the electricity, not only is it hot and dry, but the electricity is all fossil fuel generated. So the other areas we can see, Costa Rica, for example, that's hot and wet. But, so you think, oh, gosh, we need more energy for cooling, which you do. But the good thing in Costa Rica is, like Norway, most of the energy is hydro-generated. So we found some interesting points there. And some suppositions that we've made they were sort of undone, really. So in conclusion, now this is a preliminary study. We haven't considered what happens to products at end of life. Is it recycled? To what extent to the critical raw materials, etc.? For example, how many and how much of those are reclaimed? We haven't considered that. We haven't considered landfill either as a sort of alternative or benchmark to highlight the benefits of recycling. So this is a cradle-to-gate model. But the results showed a few key pointers here, that they are very, very dependent on the scope of the study. The difference in difference in energy consumption for cooling the server and cooling the data center is really significant. And then in these ASHRAE climate zones, we found that they have more of an impact on PUE than energy for cooling. That's a key point. The other thing is that full LCA and carbon assessment, the results differ. Well, we know that from the first slide I showed you. And that the benefits of liquid cooling vary according to location. That's really, really important. It's either more or less according to location. The lower ambient temperature makes liquid cooling more efficient because water temperature at less than 40 degrees means that you need less energy for mechanical cooling. So it's a sort of agglomeration of different factors here. Liquid cooling is not necessarily efficient or more efficient in very hot places because of fans, etc., which affect overall efficiency. And a key thing is that you have seasonal variation specifically in hot, wet areas. And sometimes you do have to chill water because it's above 40 degrees. But the very, very, very important influencer on all of this is the grid mix, which has a major impact on overall environmental impact. And I'm going to hand over to Stefan.
Thank you, Deborah. All right, also welcome from my side. So on the next slide, we are looking at the space on the rack level, the space in ratio to the kilowatt per IT capacity. You can see on the one side, you can see the traditional air-cooled rack, maximum up to 15 kilowatt. And there is, of course, space needed for that. Yeah, in the front, you need space for the cold eye. In the back, you need for the hot aisle. You also, if you go below, there's a raised floor, you have the ceiling. So all in all, if you look at this traditional air-cooled rack, the space needed for that is 15 cubic meters. Yeah. At the same time, if you look at the liquid cool high density rack, it's really efficient. The space is 3 times less. Yeah. It's high density, although it's 7 times denser than the traditional rack. And if the overall space of the building is 20 times less. Thank you, Deborah. So if we look now on the server level, if we look at the facility water temperature, again, I would like to start with the legacy traditional air-cooled server. You can see here the airflow, the provided airflow inlet air is at 25 degrees. This is achieved by the facility water around 20 degrees due to the mechanical cooling system in that data center design. And of course, I would like to highlight, we all talking about high performance computing, about AI. So let's say with a new generation of AI servers, the energy consumption of the internal fans can rise up to 35%. At the same time, if we're looking at the liquid cooled server, you can see here we can use inlet facility water 40 degrees, yeah, and all components are really this enabled all components for heat reuse, yeah, so also the heat rejection. So looking at this, the conditions for heat reuse are really well delivered here in this case. So, last but not least, if we look at the overall system in an overall data center facility, again, you have the traditional model, and we are really using, looking at the air-cooled traditional data center side, 130 racks, comparing this to 26 liquid-cooled racks. So don't look at the graphics there as only to give you an idea about it, to have you provide some visuals. But these 130 racks air-cooled and 26 liquid-cooled racks providing the same compute capacity. So as a matter of fact, with this model, we are really comparing apples with apples. And the liquid-cooled solution is consuming 400 kilowatt less than the traditional system. At the same time, if you look at the traditional system you're all aware of, due to the air chillers, the chillers and cooling towers, the energy consumption is 800 kilowatt. So it's 40% is really going into the IT load. So you can also imagine both systems needs a backup system. The UPSs they are provided for systems. For the traditional air-cooled system needs 200 kilowatt, and for the liquid-cooled 100 kilowatt. All in all, and as a consequence, and as you possibly also know yourself, the energy provided for the liquid-cooled is 1.2 megawatt, which is 40% less. So, as a consequence, if all existing data center sites will be changed this way, the IT load can be increased by 40% with the existing energy or the energy infrastructure. So the energy infrastructure do not need to be extended or changed. All right, all yours again.
Okay, so I think what we've tried to highlight is that it's not enough just to look at, say, servers in isolation. You have to take a much more systemic approach to this whole challenge, not just in the way that you measure environmental impact, but also the way that data centers operate as a whole. And we've got lots of work that we would like to follow up. One is to carry out full LCAs, with social aspects as well. This includes end-of-life scenarios. How is AI going to affect environmental impact because of the shift in demand for compute and energy? Is it greater than 10 times greater than non-AI work, etc.? How could this affect both air and liquid cooling and their performance and embodied impacts? Do we need to investigate in much more depth individual solutions for different geographical locations and data center types? Because it looks as though perhaps a one-size-fits-all solution isn't going to really work very well, or it could be improved. And then what sort of data centers do we design for different geographical locations? And then very lastly, we've got a couple of minutes left, which is good. Call to action. I mentioned that I led the CEDaCI project. We have developed a prototype server, which is on the OCP database. It's at the moment, it's not a complete design. We need support from server designers to really push this to become fully functioning. But we also would like to look at things like noise reduction and obviously liquid cooling, because we've concentrated on an air-cooled server. But a really, really important point here, design is something that very often gets forgotten or sort of underplayed. It's absolutely critical. If you really want to change data centers, we have to look at design, because up to 80% of the environmental impact of a product is determined during that phase. And the last thing is another output from the CEDaCI project was our circular data center compass, which please come and see me in the Future Tech area. We've got demos and so forth later on this afternoon, and come and find out more about that. And that's it. Okay.
Thank you very
so
much.
Stefan, Deborah.
Oh, 3 minutes.
Questions?
Questions?
Yeah, we do have a question.
Yeah, I've got one for you. How much does the variation in fluid, like dielectric fluid, impact the full LCA? Like the choice of fluid that's available on the market? How much research do you think has been done into that, and how much does it swing the conversation one way or another, I guess?
That's something that we would really like to know. I think trying to find primary source accurate data about cooling fluids from manufacturers is probably harder than robbing the Tower of London, because you know, we can have generic data, but actually getting really detailed granular data about cooling fluids is really difficult. As a gut feeling, and this is, you know, non-scientific, I would say that probably organic as opposed to, you know, fossil fuel-based cooling fluids is better. But again, we'd need to look at how the embodied impact compares. Does that affect the performance, the cooling performance? So there's a lot of work to do in that area, Rich.
Yeah, perfect. Thank you.